Okay, welcome to the second probe software applications webinar. I will just wait a few more seconds so that everyone has time to log on. Okay. Good. Okay, so welcome again. Welcome again to our second probe software applications webinar. Today we have Dr. Julien Allaz and me, Anette Handt. Here we will give two presentations, one after another, with a little insight into the first steps into getting good X-ray data. John Donovan, the man behind the probe software, unfortunately cannot join us, at least at the beginning. There seems he has a power outage, I guess, due to the weather, and so currently doesn't have Wi-Fi. So he might join us at a later time, but currently we don't know if he will. Good. I will start with a presentation about the first steps in acquiring high precision, high accuracy EPMA data using the Probe for EPMA software, a specialized software for acquisition, processing, reporting, everything around using an electron microprobe to acquire chemical data, and the focus will be really about these first steps to get good X-ray data. So I will not talk too much. Maybe if I have a little time. But mostly I will focus on getting good X-ray intensities and not so much about processing and the later steps. There will be other webinars that we have planned that will look at these aspects and specifically certain applications, certain more advanced applications. And so please stay tuned also to see if anything interests you in the upcoming topics. Okay, I will start sharing my screen. And I will just begin with a very few slides just to give you some background information before I will just show you how all this is being accomplished in the software. So dominantly, this will be a software tutorial. Okay, so EPMA is a very versatile technique. We are using it to get excellent, good, high precision, high accuracy data with micron level spatial resolution. It is one of usually in a lot of departments, really the start of the workflow in characterization of materials, and usually we still use it compared to something like scanning electron microscope based EDS, energy dispersive spectrometry, because we're interested in high data quality. So software usually has to cater to that, but also we are interested, of course, in productivity, and we have special interest depending on what the lab is. And so the Probe for EPMA software that I'm using in my lab is specifically catering to those needs. Oh yeah, and I should mention, of course, I forgot it. So I said my name is Anette Vanderhand. I'm at the University of British Columbia. I run the electron microprobe there, and I've been using microprobes for around 2 decades now, and I think the probe software for around 15 years. So usually the probe software is installed alongside the actual vendor software. We have two main microprobe uh, vendors. Okay, so now you can see my mouse pointer better. So we usually deal with either JOL microprobes or Chemica microprobes. We might have some additional detectors. And so usually these instruments come with their own dedicated software. That software is often quite capable for a lot of things, but specifically in a university environment, there can be limitations. And so I often like it, like we buy these $2 million instruments. So essentially you get like a race car, and if you really want to push it to the limit, you also need a software that can really give you access to all the possibilities there. The nice thing with the probe software is that it can just run alongside with the main software, so we can switch forth and back. There's no modifications needed, and we just have it running and have a dedicated screen for it. Okay, so the probe software family of software includes the probe for EPMA one that is mostly used with for spot analysis, transects, all that stuff. There's a modeling utility that comes with it, CalcXAF, that is free. Then there's also probe image and calc image there for mapping. And then there's PictureSnap app that is used for navigation documentation. And then there are a range of smaller utility programs, Standard, Drift, Evaluate, that can be useful. And they can be useful also specifically if we want to explore and optimize our analytical conditions. I will mostly focus on probe for EPMA, but might mention CalcXAF, Standard, Drift, and Evaluate. And they're really the ones that I think are important to monitor and optimize your EPMA data. Okay, so because I think we have a mix of old timers and new people that may not be too familiar with the technique. I just want to very, very quickly, this is not a workshop on microprobe as a like the theory so much, but just to pick everyone up. So we have the X-ray spectrum. Electron microprobe is an X-ray based technique. And so when we use our electron beam and focus it on the sample, we generate all these different kind of signals. We get other electrons that we use for imaging, and we get X-rays that we use for the chemical analysis. And so usually we generate two types of X-rays, the characteristic X-ray lines and the continuum X-ray lines. And that is so we usually generate both, and we have to analyze both. And this is where certain considerations for getting good data already starts. So when you look at the X-ray spectrum, so on the x-axis, we have X-ray energy versus intensities. The elements in our material produce characteristic X-ray peaks. Depending on how the atom exactly looks and how many shells we have, we often generate more than one X-ray line. So we can have K alpha, K beta, L alpha, L beta. And they occur at a characteristic energy. So that tells us which one what element we're looking at. And they are sitting on the continuum X-rays that are also produced in the sample. And the height of this, the intensities of these continuum are controlled by the complete composition of the material. So usually when we analyze our materials, we need to subtract the continuum X-ray intensity. So if we now zoom into one characteristic X-ray peak, what we're analyzing are absolute counts that we're getting. And so the intensities that we pick up are the sum of what we're getting from the characteristic X-ray and the continuum. And again, the continuum is controlled by the entire composition. And so usually, as an example, what that means is like if we have 50% iron and in an iron oxide versus an iron alloy with some other metal, the absolute intensities will differ that we're getting, even though both might have exactly 50% or whatever number you want. So we need to subtract usually the continuum X-rays, and we also have to do something what we call matrix corrections to account for differences in X-ray production and X-ray emission. Okay, so how do we do that? In EPMA, we analyze, of course, the actual X-ray intensities, but then usually we also have to analyze at the backgrounds. And so we don't want to acquire the entire peak. We instead analyze just two positions, a low background and a high background, and try to fit that as good as possible. And the second talk will go into much more detail in all the different ways how the software allows to analyze this background and to process it. I will only show a little bit about that. But that is a very important part if you have complicated samples or you want really high precision, high accuracy data. So Julien Allaz will talk about that. Okay, so in the machine, the X-ray detection by WDS occurs by using Bragg's law. We have analyzing crystals in the machine. And with Bragg's law, what happens is that the incoming X-rays essentially get filtered so that only the characteristic X-ray line of interest actually gets then refracted out into the detector. So instead of analyzing all X-rays at the same time and tells us about it, like what an EDS does, we achieve better precision by just looking at one at a time. That improves the background usually drastically. And we also get better spectral resolution with this technique. And so but it also means that we usually have to know ahead of time or at one point in the process what exactly we want to analyze, because instead of just saying like show me whatever is there, we have to say, oh, I want this element and this element and this element. How does that look in the actual spectrometer? We have an analyzing crystal and we have a detector. And that will be important in terms of what the software asks us, what kind of information it wants to give us. It needs, and it's also important in terms of like what kind of tuning usually we have to do. So here's a look into the actual spectrometer, and again up here is the analyzer crystal and the X-ray detector. So because we have to move that spectrometer, we usually have to analyze everything sequentially. So we have to move the crystal to record the entire X-ray spectrum. Again, if we do spot analysis, we just analyze usually 3 positions in the most traditional way, what we call the off-peak method, at the peak, and then 2 backgrounds. And then if we have more elements, we usually analyze them one after another and stack them up. There are different crystal types usually, And so these are their different acronyms. It depends very much on each individual instrument that we have, how the layout of the machine looks like, and what crystals are available. Each crystal brackets a certain part of the spectrum. So up here is essentially the periodic table, and then these color bars show the range of each crystal type for K X-ray lines, L X-ray lines, and M X-ray lines. And so usually when people buy an instrument, they try to get a something that works for a lot of different applications. And we can have up to 4 crystals per spectrometer usually, and up to 5 spectrometers on a machine. Okay, good. So I want to talk about I will show you how it works for routine analysis, but also we'll talk a little bit how we can improve high accuracy and how we can improve accuracy and precision in our analysis. And just from a philosophy point, again, usually we care often about trace elements. And so certain things can become more important depending on the application, depending on what we're trying to analyze. And so I just want to point out a few things which are like our gears that we can turn to help there. So when we analyze major elements, usually we have a very high peak to background, and the background positions and the fit are meaningful, but we have a little bit more, like, I'm not saying like they don't matter, but it's a little bit more forgiving. Versus if we have trace elements where we have a very low peak to background ratio, and then your background analysis becomes just as important as your peak analysis. And so if we want to either analyze major elements more accurate or just, let's call it better, the same thing applies, but yeah, specifically if we push it to low abundances, that becomes a very important topic. Same if we do trace elements, we usually have poor counting statistics. And so things like count times and the instrument tuning becomes important. And also, if we analyze very simple materials, meaning there are very few elements compared to very complex materials where we have many elements, things like interference corrections, background positions, background fit type, all become really important. And then at times, one of the things where the microprobe really excels is the analysis of light elements, or specifically light elements in a complex material. And again, interference corrections are important, background positions, but also matrix corrections matter. Good. So let's actually start with the software then. So when we usually run the probe for EPMA software, and when we started it, again, it sits piggyback on the actual instrument, and the first question is, do you want to interface to the microprobe hardware? I'm not in the lab right now. I have analysis running, so there is a demo mode that allows me to use it for a webinar like this, but also you can train yourself with it. You can use it as an exploration tool, and so it's very useful. So what I will show you is still exactly applicable to how it would be if I would be directly connected to a microprobe. So the first thing is, do you want to interface with the micro hardware? Usually the answer is yes, but I mean, sometimes you just want to process data, and so in that case, you can just say no, and it will just open the processing mode. So I say yes. The main window, I will maximize that a little bit. And in general, here in the lower left corner, it tells you what it's currently doing. So there's like a running commentary. So if you wonder like, oh, does what's going on, it's always worthwhile to look down here, like, and then it will say like it's moving something or it's connecting or whatnot. Okay, then we start with making a new file, of course. And I just put that here on the desktop. And so I just call that PFE webinar 2 setup and say save. And the first window that opens is a little file information dialog that I tend to not fill out, but you could. And there's a little utility tool that can read out all that information. You can search over it. So if it's important how you bill or how you keep things, it can be very, very useful. Okay, good. First, a few words about the structure of the software. People who already used it are sometimes a little bit terrified on when they see it the first time, because again, the idea is that it's very capable and very versatile. So there are a lot of options. There's not really a dummy. You can only have 3 dialogues and they do 2 things kind of software, but there is a structure to the madness. So we have 4 main windows. Acquire, which is usually everything that is important to set up an analysis. Analyze, which is where when we have acquired data, you will find the data and you have like all the processing options in there. You have automate that allows you, that controls your positions that you like the standard positions and where you want to analyze. And then on the right hand side, all kinds of automation actions where you can like I love automation where you can set up everything and just let it run over a weekend or overnight. And then there's plot, which is mostly just for wave scans to look at the data. So we will mostly use acquire and then a little bit automate and plot. And then all the options here on the top are more global variables where I can turn certain things on or off. Most important, analytical has like options, matrix corrections. Julien will talk about man backgrounds and other types of backgrounds and so on. Then run is to list and display data, and output is to export and save and all kinds of things that you want to have as individual files. Okay, so I said acquire is where we need to set up things. And so you can see a lot of it is grayed out. There are a lot of options. And oftentimes there is a very specific workflow that we need. And so there is a new function under File called Basic EPMA that is essentially a link collection. So none of these buttons is unique. It's more like it's dialogues and windows that are in acquire, analyze, automate, and plot, but they're ordered in kind of the workflow how you would usually work. So Basic EPMA is a very nice tool to have users use, or if you just want to follow. You see certain buttons are yellow. And so these are usually the ones that you definitely need to hit, and other ones are where you might just want to change your defaults. So the first thing that you need to do is make a new sample or sample setup, because this is based on a database. And so before we acquire any data, set anything up, it needs to know where to save the data to. That has also the advantage that if something crashes, which it doesn't do that often, but stuff happens, everything is immediately saved. So you never lose data. The first thing that we always want to do is create an unknown. So it distinguishes between standards, unknown, and wave scans, and we will see why. And so the first thing that I usually just do is say setup. Okay, so that just created an entry for the database, and now it knows where to file things. The next thing that I need to do is I need to tell the software what elements I want to analyze. So I go to Elements Cations and I click in any row in the next dialog, and that opens the Element Cation Properties window. Okay, so the first thing that it asks is everything about the element. Then below here, we have everything about the spectrometer. And then down here, I can check for interferences already. And then everything on the right-hand side is about different types of backgrounds. Again, one of the strengths of the software is that we have so many options. And so Julien will talk about it, but for this purpose here, we will just look at the left-hand side. And down here are also things that are useful specifically for light element analysis, like area peak factors and integrated scans. Okay, so I want to analyze a very simple chromite. So I have a few elements that I want to analyze. So I first enter the element, and you see it auto-fills the next steps. And these are all defaults that I can set in a text file. I can say I want to analyze it. I can also say that I just want to specify it later, and I can say that I want to analyze it by EDS or WDS. Then the next thing is that I have to tell it what spectrometer I'm using. So spectrometer 5, again, it auto-fills based on defaults, and it can calculate where the peak position is, and it gives me some recommendations for off-peak positions and detector settings. I can check if I have peak interferences, but of course, so far it only knows that I want to analyze iron. So it's not that useful at this point until I have entered all the elements to really check anything here, because it doesn't know about the other elements. So oftentimes a good workflow is not bother with that and then circle back to when you have everything entered and check it. But of course, an even better way is to do actual wave scans. Okay, so I have iron. I want to analyze chromium in my chromite. And so we just go through this and just take the defaults. And I want to have magnesium on the TAPL. And I want to have aluminum on my TAP. And then a classic example of an element that we don't want to analyze because we know it's stoichiometric, we can say we just specify it as oxygen. Other examples are carbon and carbonates. And again, otherwise I can also already put in to use the EDS, because you can do integrated EDS, WDS analysis in the software. So this would be, oh yeah, and titanium. Classic, example. See, and if you're thumble-fingered like me, you can also just use pull-down menus in these, but it doesn't have, it's all lowercase, which I hate. So I don't do that, but you might want to do it. And then sometimes it doesn't autofill, and so I can still switch around everything. I can choose other X-ray lines, I can choose other Bragg orders, and I can also define the stoichiometry different. I can also say later to disable acquisition or disable quant in here, so there are many different options. Okay, so the next step is usually that I need to assign standards to it. It always very helpful tells me that there are none yet, yeah. And so that gets us to the standard and interference assignment dialog. And then here I can do add remove standards and have my entire standard database. If I, for example, just know what I want, I can just search for the name and look through all the spinels that I might have, or maybe I know the number and can use that. You can also in the database set up different types of, you can filter it for different types of standards. And so with that, I can add whatever I might need. Or there's also a trick, if it's a lot of elements and you have certain classical setups, I can just load in a pre-organized list. Okay, let's take these out again and load in chromite, and then I already have them. So I say, okay, and then I could go in here in this dialog and assign them all one by one. But who has the time? So instead I can say reload standard assignments. And what it does is it just looks what the highest concentrations of the elements are in the standards. And that's usually what we want. So then it assigns whatever is the highest of the ones that I added to the run. If I want to modify that, I can still do that. So I could switch things around. And so if you have a lot of standards, that's usually like a nice quick way to get most of them assigned, and then you can micromanage them. I mentioned interferences. So that you have to worry about interferences with the backgrounds. You have to also worry about interferences underneath the peak. So in the software, you can search for them and see what is there. So for example, there's interferences with higher order lines for iron and chromium that might be important in a material like a chromite that is very high in these elements. So I can use that, and I can say, oh, I want to do a fourth order. I want to acquire intensities to use these into combination to correct for these. And so I need to use a material that does not contain that element, so it analyzes the aluminum intensities that it's getting from an aluminum-free material, and thereby we know that in this case that would be really the fourth order iron. And as you can see, I can have up to 6 defined in here. It gives me some idea how bad, how good they are. Again, the best is always to do a wave scan to really see how realistic it is. The higher the order, the lower the number, the less you have to worry about that. But sometimes it can be meaningful. And again, for high accuracy, high precision data, you really want to make sure that you have all that. Okay, so I have my standard assignments. I need to assign analytical conditions. So chromite, maybe I want to do 20 kV, 20, and I want to have sort of a focused beam. It allows you to set spot or scan. And so I can just do it. And again, down here, it says that it's in simulation mode. It's setting these settings. Then next step, okay, and it's really doing the simulation, so things take a moment. Next thing is I want to adjust the count times. So there's a dialog for that here. If I want to change it for all of the elements, I click on the tab up here. So I can change that, and it changes for all the elements. If I want to have them individually, I click on the line and can have that changed, so thereby I can build my setup. And then there's something relatively unique here, because you usually define a setup that works for both the standards and the unknowns, your samples. But the one thing where you usually want to really analyze them differently is that your standards are very high abundant, have a high abundance of the element. So you don't need to analyze for very long, but your unknown might have it at trace or minor element level. So there's an unknown count time factor that you can assign, where if I, for example, say 10 seconds on the peak, 5 on each background, and I put in an unknown count time factor in of 2, what it will do is it will analyze the standards with 10 and 5 and my unknown with 20 and 10. So that's a very easy way to then automate a lot of analysis. And it tells me what the total runtime is, and again, also other things like return to on peak. So this is the start of the analysis, and then it says it would take 57 seconds with all the spectrometer movement and whatnot. Okay, so we've done our count times, then there are acquisition options. And this is now a point where, okay, sometimes I just don't want to do 4 elements, but I want to do many elements. And I don't want to enter them every single time when I do. So the software actually has the option that I can load in file setups that I used before. So again, I just go back to my new sample setup, make a new unknown, make like, I don't know, another setup. And then I go and load file setup, and that allows me to navigate to wherever I store my things. And I go to chromite analysis. And here is my chromite setup. And it shows, no, let's go in here. There's a lot of data already in there. And I can load in my a full setup with many more elements that I've been using. And it shows me what the conditions are and what the elements are. And then I can say, okay, I also have the option to load in standard intensities if that's something of importance. If they're not already loaded, I just say no because I just want to have this set up, but otherwise I could do that. So yeah, I sometimes switch things with the new dead time correction. That's what this thing is. So, and then if I go back to my elements cations, now I have many more elements in there, as you can see. And if I look at my count times, you see that this is like a setup that I'm using for like a more full analysis of the chromite. Why is that also important? In acquisition options, sometimes you want to change the order in which you acquire elements. And so acquisition options is the place where you can do it. You can either have like ascending, descending, if you don't care so much, you just want to optimize your spectrometer movement, or you can say user-defined order number, where you can literally go in and say, no, I want to analyze something else later, and so on. So if you want to analyze sodium first, you can define that here. In addition to setting also the EDS elements in the elements cations, you can also just say acquire an EDS spectrum with everything. So when we have that, and of course, got 40 minutes, never enough time. So I just show you quickly. So the next thing that we usually need to do is then peak the spectrometers. So we can acquire, we can peak the spectrometer, we can do PHA scans, which is peaking the detector essentially, and can do that on the standards that are assigned, or we can do it manually. And so if I look, if I just look at the peak scans, and I should have loaded, and I just quickly switch, just like in a cooking show, to the actual file where I have data. So then I can look at the scans. I bring up basic EPMA in a moment. The software records everything, and I can look at it and I can verify what's there. And so this is really excellent to keep a record, but also then to have that making sure that everything is working as needed. Okay, so when we've done, if we have the spectrometer peaked and the options done, then we can theoretically go in our unknowns, and we can set up points that we analyze at different places. We can do that by either just navigating to it and adding single points. We can add traverses, and we can also digitize images, and we can set points on the image. If you do a lot of homogeneity testing, there are also options for that. So overall, there is a lot of ways how you can do it. You can, this is just a chromite setup. I can also have, if I want to analyze multiple phases in a given sample, I can create multiple setups, one for chromite, one for feldspar, one for pyroxene, and can then, to the positions that I acquired, assign setups, so different recipes. I can also just, if they all have the same spectrometer layout, but I want to modify conditions, I have options, and I can assign that to all these different analysis, and then just run the standards and the unknowns. Okay, I'm really running out of time. One thing that I also wanted to show is we can acquire wave scans, but I can also load in wave scans from a different run. And so I can just go somewhere and say like, oh, I had a wave scan there, I can load it in. Or you can acquire it directly. And then when I look at the plot window and want to like fine tune my analysis, again, this is something that Julien will probably show you much more. I can look, and for example, with the titanium, in terms of high precision, high accuracy, I see the wave scan. Here's my titanium peak. I can model the background. And you see, when you have a linear background, you're actually cutting out, I don't know, 15% of your intensities. So that's where the different backgrounds can really come in, and you can optimize that and have it then assigned to setups as needed. And so you can do that and can look at your data in various ways, and even for major elements that can sometimes be useful, because, okay, so in this just linear view, that looks kind of good, and I model my background and the linear looks good. But then in terms of position, if I have the options to go lin log, so I look at it in log scale, sometimes I can see like, ooh, maybe it's a little bit too close actually, and I should move my backgrounds a little bit further out. And so I can just set them here, double check that I like it. And then it will be applied to the next open output. Okay, so that was a speed run through many options. But again, it's, if you have routine analysis, it does all the things that you want, but it also records all the data. Everything is saved in a single file, including the standard acquisition data. But if you specifically, if you want to push it, if you really want to check things, all these options become very important. Okay, so again, this does not replace a training. We have a YouTube channel that goes into more details. So I will just stop here and see if there are a few questions. We're already going, of course, into the break. So sorry about that. And let's just see. I see no open questions. If you have any questions, put them in the Q&A or put them in the chat. But otherwise, we can also answer questions at the end. So 3, 2, 1. If nothing comes, then I would say we break for, Julien, shall we do 10 minutes to give people?
10 minutes, or if you want to stay on time, I don't know, it's equal for me. We can do 10 so that people can get a cup of tea or so.
Yeah, and process. And yeah, if you during the break have already questions that you want to put in the Q&A that I can answer later, or that maybe Julien already can address in his talk, then feel free to do so. Okay.
All right, so let's see us at what is it? 9:55 a.m.
Yeah.
Pacific time. All right, see you soon.
Okay, we're back. I hope
And
everyone
back
had a
through.
time, and some people also had some questions already, so check out the chat. And specifically, of course, I ran out of time and didn't show you how to check for precision and accuracy of your data. And so after Julian's talk, I will just show you that very quickly. But now we have Dr. Julien Allaz from the ETH Zurich. He is also a longtime microprobe specialist and user of the probe software, and specifically a specialist when it comes to all the ins and outs and details of background positions in the software. And so he will tell us all about it. So
Thank
thanks,
you, very
Julien.
nice. Thank you, Annette, for these very nice introductions. I'm going to start sharing my screen here. And as Annette did, I will start with a brief introduction. So again, we don't want to go into too much theory, but I'm going to show you here today that Pro for EPMA does offer you a lot of versatility in terms of acquiring backgrounds. So in theory, we should rather speak of bremsstrahlung, I should say, because the background is not really a good word. So the bremsstrahlung is a signal. It's a signal of this X-ray continuum, the breaking down of the electrons in the matrix. And we need to account for that because this is not the signals we want to measure. We want to measure the characteristic X-rays. So most of the software do offer just simply an off-peak measurement. So we'll see that in a minute. These are very simple basic measurements, like Annette mentioned, where you do acquire the peak and then two background positions. But you will see that Pro for EPMA does offer different technique. So let's dive into that. We do have first this classical 2 points background offset acquisitions that is available with Pro for EPMA. And we can normally do classical linear interpolations. However, there could be problems and cases where you have to use only one side of the backgrounds or the other. This is also possible with Pro for EPMA, or you can constrain only one side of the background position and force a certain slope. You can also potentially apply exponential and polynomial fitting, which are options which are not available always in all software from the microprobe. Of course, when you consider only 2 points and you would like to have a curve with an exponential or polynomial fitting, you will need additional parameters. But we will find some ways in Pro for EPMA to actually acquire and obtain these correct fitting parameters. Another option, which, to be honest with you, is what I use 95% of the time on my microprobe, is this mean atomic number background correction. This is something that will save you a lot of troubles. This technique relies on the dependency of the bremsstrahlung intensity with the increasing average atomic number, Z bar. And so this is known since a long time, but it is now implemented in Pro for EPMA. It's a very simple and efficient, and for most applications, down to at least 200 to 500 ppm. After that, you may start running into troubles regarding accuracy issues. And these accuracy issues for trace elements, so elements below 100 ppm or so, will be somehow resolved in simple matrices by applying a blank correction. So I'm not sure if I will have enough time to go through these blank correction options. This might be reserved for another seminar. Another options that actually, thanks to John Donovan and also to my colleagues here at UMass Amherst, actually, when I was a postdoc in Massachusetts, John and Mike Jacenovich and Mike Williams worked together to develop this multi-point backgrounds. And actually, that was part of my postdoc work to develop this approach. So this multi-point backgrounds approach is very good for excelling in trace elements analysis, especially in very complex matrices. And I will show you an examples of lead analysis in monazite. And this is a trace element analysis problem in a very, very complex matrix with a lot of elements. So these multi-point backgrounds options offer the possibility to choose up to 12 offset positions on each side of the peak. That might be too much. Most of the time I use like 4 to 5 on each side. And it helps you indeed to constrain perfectly the change in the bremsstrahlung intensity over your spectrometer range. This technique has also another sidekick, if I can say, which is called the shared backgrounds method. With this shared background methods, we'll see maybe if we have time, this options allows you to consider multiple backgrounds you would have acquired on one single spectrometers, like for instance, a series of 2 points backgrounds in multiple elements on the LIF monochromator. And you basically consider all these backgrounds that you have acquired independently of each others. You consider them all and constrain actually the bremsstrahlung intensity over a large range of spectrometer range. So another options also that is available in Pro for EPMA is about a calibration curve. So that's an applications that would be specialized for instance, carbon or nitrogen in steel, where you acquire multiple standards of a known carbon or known nitrogen content, and you use this curve to calibrate the carbon or nitrogen content, and then analyze your unknown. However, I doubt we'll have time for that, and I'm certainly not the best specialist to present you about this approach. So the 2-point backgrounds, we'll try to keep it very short because I'm sure most of you know about that, and Anette von der Handt did a very nice introductions about that. It's an acceptable method, yet you have to be careful. You have to choose indeed background positions that are free of any interference. And indeed in the chat, we had some questions about how to choose good positions for the backgrounds. Well, this is you as an analyst to be responsible to choose a position that is free of any interference. And you will see that sometimes getting wavelength dispersive scans is very, very helpful to try finding suitable positions. The linear fitting is usually a good approach, providing you have a good peak to background ratio. And if you don't have a good peak to background ratio and you start dealing with trace elements, you will see that curvature becomes a problem. And there you'll have to deal with fitting parameters of exponential or polynomial to constrain indeed this curvature of your bremsstrahlung. The problems of these 2-point backgrounds is that ultimately it takes time. You spend only half of your time measuring the true intensity you want, which is the characteristic X-ray, and you have to spend equally amount of time to get these backgrounds intensity. Also, you add a lot of uncertainty because, of course, the total uncertainty is depending on the sum of the square of the peak uncertainty, the peak measurements uncertainty, and the background measurements uncertainty to the square root. As your background's intensity is very low, your precision will be relatively low, and your background uncertainty is dominating your overall uncertainty. So we'll see how we can improve that. There could be also problems of inaccuracy because of beam damage. If you take, for instance, some glass, you may start analyzing your peak positions for sodium, and boom, your sodium diffuse away. What happens is that your matrix simultaneously will get denser. And as it gets denser, you will increase your background intensity, your bremsstrahlung intensity. And therefore, if you measure your backgrounds after the peak measurements, you will get an inaccurate measurements of your bremsstrahlung intensity. There could be also problems of inaccuracy for trace elements analysis, again, due to the very strong background curvature. And we'll come back to this in the last part of my talk when we talk about multi-point backgrounds acquisition. There could be finally inaccuracy from possible minor interferences that you may have forget, or even absorption edges, which we tend to underestimate, especially when we deal with trace elements. So the simple case, peak to background ratio is over 50. You take 2-point measurements on your backgrounds. You assume a linear fitting in between both. And even if you zoom in and you look that, yeah, okay, there is a little bit of curvature on my backgrounds, this change here of intensity compared to the huge peak intensity you have will have almost no effect. And I show you that here very roughly with a simple calculations. We assume that we have an intensity of 50 counts per seconds per nanoampere on the peak and 1 on the backgrounds. Now, let's assume that your background's measurement was wrong. And then you decide, well, it may be 1% less. If it is 1% less and you calculate again your new net intensity, you will have a change of merely 0.02%. Even if you are wrong with your background acquisition by minus 10%, it merely changed by 0.20% the overall net intensity on your peak. So basically, this uncertainty that you have on the approach of linear versus curved is almost not visible. It will be mostly within the uncertainty of your own measurements. So this is usually not a problem. So I'm going to show you here now a first example. This very first example is simply a plagioclase analysis. Have loaded here my file already, so I will not go into too much details about how to use the software. Annette did introductions. I'm just going to dive directly into the subject and here open this acquire window where I set up my conditions. So I'm going to create a new setup just to show you how things are done. So this will be a setup random. And I have here already all my elements because basically I had already analysis in this run and it takes simply back the setup that I had before. So you can already see in this acquired specified elements window that we do have the list of elements, and you see here the types of backgrounds that you are currently using. And so if I click on any elements, we have several sections that interest us. First thing first, these big sections over here, this is where you choose the type of backgrounds acquisitions that you want. So at first, we will deal with this off-peak backgrounds section, this backgrounds option. With this comes a series of different fittings that you can use, you can apply. You can apply just a linear fitting, an exponential fitting. You will have to here specify the exponential value. You'll have the slope options here. You can also choose just to get the average of both backgrounds, or consider only one background side or the other, or also choose some kind of polynomial fittings where here you'll need to define several coefficients to do the fitting. But let's keep it simple, and for the moment, we'll leave it at linear. Now you see here that we do have two background positions. In my lab, what I did is basically we are analyzing a lot of silicates. Most of the times we are analyzing the same elements, and what I did was simply acquiring a collections of wavelengths dispersive scans in multiple standards that have many of the elements that I want to analyze. I simply overlap all these standards, all these wavelength scans, and basically define these positions, which I know for my silicon K alpha will be interference free. If you have any doubt, like Annette mentions, you can click here on high off-peak interference, and it will list you here the potential list of elements that could interfere and their X-ray lines up to, I think here, the 5th order or so. And yeah, so that's the first options you have here to evaluate the backgrounds and try to choose the best position. So again, this is just a simple case. This is something you can do with any software. We can have a look briefly at this plot window. In this plot window, I did acquire a scan in the samples that I had to analyze, which is an almost pure albite. And I can, for instance, here have a look at my sodium measurements, my sodium wave scans. And of course, I will have a ginormous peak. So you'll excuse me, this red line normally should be right in the peak, but I had some issue during that run. I'll pass on the detail. But point is that you can use this plot window and this acquisition of a careful scans around your sodium K alpha to choose the optimum positions here in green for your backgrounds. And I can zoom in a little bit even closer. And I could potentially, using this window, define new positions. Like for instance, if I want to get my position a little bit closer, I can set it here. I can click here on my high button and set now the high positions, maybe a little bit further away from the peak. And I can model my background. So modeling your backgrounds is very, very helpful because if you imagine that you want to have a certain curvature, you need to understand that this must be specified. You must specify a certain exponential parameter. And in this case, of course, the background does not seem to be so curved. So this is not a big issue. So rather than spending time on this very simple setup, where every element is very easy to acquire, because you can see that even for my calcium, which is as a trace elements in this albite standard, we have here the two positions that I opt for and the peak position here in the middle. And effectively here, I think even if you apply a linear fitting, you'll still get an accurate measurements on your calcium. Let's just now switch briefly to another setup where I decided to try acquiring rubidium, barium, and zirconium in glasses. So this is a more complex analysis because we are dealing with traces. And well, I just have a warning here because it's a very old file that I used with a very old version of Pro for EPMA. And it's warning me that I should not consider anymore this file, but it's for an example. So here in this example, here I have a, oops, I will choose, for instance, just any of these. I have here a setup where basically I'm analyzing these trace elements, rubidium, zirconium, barium, and I just have a few major elements. The other elements are constrained by being specified. So I give the composition of the glass. I do not analyze the major elements, except for indeed these 2 or 3 elements, silicon, aluminum, and titanium. The point is that we do expect ppm levels of this. And so I have to be very careful with my background. So I tested here, and just going to show you here a scan of my barium titanium oxide and looking at the rubidium in these standards. I expect no rubidium in it, so that could be a good standard to analyze to test for a blank. That is, can I precisely measure the absence of an element? And that's a quote from Magdashinovic. If you want to do something very, very good in terms of trace element analysis, you first must demonstrate that you can precisely measure nothing. So let's have a look at this barium titanium oxide. Looks rather clean. We have here the wave scans around the position of rubidium L-alpha in spectrometer positions for gel and intensity here on the TAP monochromator. You see that we are on the very low side of the TAP. And in that case, the background is very curved. And so that's in these situations that you absolutely need to do a correct backgrounds modeling. You'll also notice that here we do have small peaks. Are these significant or not? Well, you have a way here to check it. You can, on this side, select certain elements. So I can, for instance, specify some elements. I know that I'm analyzing a barium titanium oxide, so I do expect some barium. Let's type in barium, and ta-da! This X-ray line is your barium L-alpha 3rd order. So despite the fact that I use here the differential mode on my spectrometer, the 3rd order barium lines is still visible. So, sorry, I pushed the button I should not have pushed. So we need to be careful and not place the backgrounds at this position. So that was where originally the background was, and now I have to place it rather at other positions further away from this possible interference. There is also another peak here, and it's actually not a surprise, but it's also titanium K-alpha 3rd order. That's our classical interference of barium L lines with titanium K lines. So that's the first problems we have to deal with, making sure that we choose a background-free, an interference-free background position. The second point, I hope you realize here that our backgrounds is extremely curved and we need to account for that. So let's go for the background modeling option. We have here a linear backgrounds, and if we were to analyze here linear backgrounds interpolations, we would have a background intensity that would be much, much, much higher than what it should be in reality. So you will have here a big inaccuracy error. So instead of that, I will, for instance, choose an exponential fit. And for instance, in that case here, an exponential fit of 1 seems okay, but tendentially we are a little bit too high here, a little bit too low here. So we can try to play a little bit. And if we choose, for instance, a modeling of 3 or 4, this would be acceptable. So here we have a way through the acquisition of this wavelength scan to constrain the background curvature. This is, however, here just an, I would say, qualitative approach, and this may not be the best way to do it. So I'm just going to leave this aside for the moment, come back to my presentation here, and I'm sure we'll find a way to get this PowerPoint available to you if necessary. But this is here just a summary again of what I just presented. So we deal with the off-peak background measurements. This section is all about setting your off-peak, how you want to set it, and how to check your interferences and how to set your background position. Now, the problems of the background curvature. With trace elements, you need to very, very carefully place your backgrounds and determine your backgrounds. And as you must constrain this curvature. As an example, similar to the former examples that I show you, if we have a high peak to background ratio, no problems, you will not affect so much your total net counts. But if you have a peak to background ratio that approach 1, like for instance, in peak intensity, raw peak intensity of 1.5 counts per second versus a background of 1, then if you have a change of 1 or even just 1% on your background's accuracy, then you'll have a 2% inaccuracy error on your measurements. So it becomes very, very important to constrain this curvature. So we have two options to do that. The first one is also very good options when you have extremely complex backgrounds. I mean, the backgrounds, very complex spectrums, like for instance, this rare earth elements phases. There are here two problems. First, the background is curved. You see here, actually, it's a linear relationship, but we are looking at a logarithmic scale. So we have here an exponential fitting on the backgrounds. And the other problem is that there is no way that you can find interference-free positions, especially in the range of the heavy rare earth elements. So how can you deal with that? Well, you do not measure the backgrounds. And this is the principle of this mean atomic number background correction. So we have this option here. And rather than spending time on this slide, I'm just going to show it to you live with yet another run. So closing this file, reopening another one existing. And in this file here, this is my kind of versatile conditions, I would say, for any silicate analysis. I simply have here my 10 major elements that are constituting almost 95% of the minerals you can find on the Earth crust. So silicon, aluminum, calcium, sodium, potassium, iron, manganese, magnesium, calcium, chromium, titanium. That covers basically most of the minerals. And look at that. I can get one analysis point in 83 seconds. How do I do that? I measure only the peak position. So if I were to click here on my counting time, you will see here that I count only 30 seconds on the peak, but my backgrounds here is grayed out. How does it work? Well, if we look at the standouts, any standouts that I have acquired, for instance, here my rutile, I actually acquired every element in my rutile. It sounds like stupid, right? We lose a lot of time. We could count only 30 seconds on the titanium for the rutile, and that's it. But here, in that case, I actually measure every element. And if I consider, for instance, the measurements of the sodium in my rutile, I have actually no sodium in the rutile, and there is no X-ray line interfering my sodium K alpha. So the measurements that I have here, which again is peak measurement only, this measurement corresponds to a measurement of the bremsstrahlung. This is my background intensity in rutile on the sodium K alpha. And the same goes for every element, providing, of course, we do not have the element present. So after acquiring all my standouts with all my elements, you'll notice here that I have acquired also standouts that I actually do not use as a primary standouts, like my corundum. I tend to prefer the anorthite for the aluminium. I have analyzed also quartz. I have also analyzed the periclase, magnesium oxide. All these, I don't use them as primary standouts, but these are simple oxides which do not contain any other elements. So they are extremely valuable and good for us to fit indeed this background curve. So how do we get this background curve? We need to go here in the menu analytical, and we have these first options to assign this MAN fits, mean atomic number background fits. We click on that, and the software will go through each of my standouts, determines which standout does not have this or that element, and ultimately it will pull out these different curves. So I have my elements here that I want to analyze. And for each element, you see a plot of the intensity of a certain X-ray line versus the average atomic number of the standouts we measured. So each of these green dots are standouts, and these are standouts that do not contain, in our case here, silicon. So I have the corundum, hematite, rutile, and so on and so on. So I have measured the bremsstrahlung intensity in different standouts that have no silicon, and this The relationship here is simply the expected relationship of the increase of bremsstrahlung intensity versus the average atomic number. Notice that this is also corrected for absorption. So I have normally an option here where I can show what happens if I do not correct for the absorptions. And if you don't do so, you'll start having some shift because indeed, of course, the intensity of the bremsstrahlung will be a function of the matrix. So you need to correct at least for this absorption effect. So this effect of absorptions will be strong on light elements. I think on the sodium is one of them that shows you the worst. There we go. So if you don't consider the absorption effect, you don't get any relationship. So we must correct for this absorption effect. And there we go. We have a perfect fitting with many standards that are sodium-free. I can even plot the uncertainty at 3 sigma level. Of course, we are dealing with a background, the bremsstrahlung. So we look at a statistic at 3 sigma. So this is now defined. We have here all the elements that have a certain background curve. And now that this background curve has been defined, we can go ahead and analyze any unknown. And let's say we analyze an unknown which ultimately comes with an average atomic number of 14.5. At 14.5, we take this curve and we know that the intensity of the manganese K alpha bremsstrahlung in materials of a density of 14.5 should be exactly 0.96, something like this. And you can see that this curve is actually constrained by many standards. This means that we also improve strongly the precision of the measurements. Rather than relying on rather imprecise background measurements with 2 points that are acquired with half the times we need on the peak, here we rely on a curve which has many standards. So naturally, the uncertainty here will be very, very small compared to a 2-point background acquisition. So that's how it helps us gaining precision. In terms of counting time, now that we don't need to count on the backgrounds, you can get exactly the same data that you had before, but in half the time. The only downside, as you can see here, is that even if I have only 10 elements to analyze, I will need a little bit more than 10 standards, or maybe 8 if you combine elements on multiple standards. And the reason for that is that you need additional standards like indeed this hematite or this periclase or corundum, which are free of any element. So that's brief introductions about the mean atomic number. Before we switch to the last and not least options, I just want to show you, so yeah, this is just a summary slides telling you exactly what I show you now. I just wanted to show you here a comparison of several data that I got in the samples with the mean atomic number background corrections and other data that I acquired with the backgrounds. And basically, these data are identical. So you get exactly the same value. A cool thing also about this mean atomic number is that, computer is running slow. Apologize for this technical issue. Hello. Does someone has a song to sing? There we go. Okay. So the cool thing with that is that it is quite accurate. If I just have a look, for instance, at a bunch of my standards here, secondary standards, RNL homelands, I can combine all these analyses that, again, were acquired with the mean atomic number background correction. I can check if I get good data, and I can ensure you'll get very accurate results and precise. I just want to show you especially the chromium. So this RNL homeland should not have so much chromium, if not at all. And you will see that we can achieve actually a quite good zero value. Just have to be patient a little bit. There we go. So actually, well, maybe it does contain a little teeny bit, but this is getting a little bit to the threshold of what Pro4EPMA can do with the mean atomic number background corrections alone. That is getting down to less than 200 ppm. but it can normally very nicely show you the presence of any elements and precisely and accurately measure them down to 100, 200 ppm, shall we say. So with that, I have my very versatile setup. I can potentially, if I were to analyze, for instance, titanium in quartz, we have the problems here that titanium in that case would be a trace element. Yet you can still potentially use that. And what you would do, for instance, well, this is not a quartz analysis, but let's say this would be a quartz analysis. And if you were to measure the titanium with the mean atomic number, you expect maybe a few ppm Lodel, 150 ppm, 20 ppm. So the mean atomic number is usually not suitable. But what we can do is that we can choose actually a standard. Maybe what I should say is briefly opening actually a true run of titanium in quartz with the mean atomic number background correction. I think this is a very cool thing, and John Donovan had a very nice paper about that. This will be inside. No. Can choose any. I just hope this is a good run. This was a student run. So what I did here, for instance, is first I have acquired actually a quartz standard. And that quartz standard is actually a reference materials. There it is. And this quartz standard has actually no titanium, almost nothing. It's a hydrothermal quartz. And what I did is that for the unknowns, which are here, I go in my standard assignments, and here for every element, I choose here a so-called blank standard. So this will correct for the possible inaccuracy of the mean atomic number background correction. In the case of titanium in quartz, the main reason for this inaccuracy comes from the fact that there is actually a negative peak under the titanium K lines, and this is due actually to a double diffractions within the monochromator. So this is a problem because you constantly get negative 20 ppm or 50 ppm, and you need to correct for that. And so by setting a blank correction, we set basically standards for which we say to the software, we must have 0 ppm, or we can write down, I know that this samples has 10 ppm, for instance, and the software will correct my unknowns, assuming this should yield 10 ppm. So it will correct for any shift we would have in terms of inaccuracy due to, for instance, these negative peaks. So with that, I'm going to leave aside the mean atomic number, maybe just by briefly mentioning that if one day you have actually only off-peak measurements, 2 points backgrounds or so, you can still use these off-peaks to actually generate MAN fits. And this is simply using the interpolations of the two backgrounds intensity to be used in this mean atomic number background fits. All right. Last but not least, I would like to go through the discussions of the, well, so that was the blank correction. So yeah, if you want to have more details about the MAN backgrounds, John published a paper in 2016. You have the DOI here, and I think it is also listed on the Pro4EPMA website. So we will finish here with a complex case, which may not be the applications for most of you. I'm going to speak here to you about precise and accurate trace element analysis in very complex matrix. So imagine here a very synthetic spectrum where we have multiple peaks. The peak of interest is here, right in the middle. And this peak, unfortunately, is sitting right on the edge of many, many other peaks, some of them being like major elements, for instance, which provide you here with a big issue. Like, for instance, in between these two peaks, the peak of interest and this major peak, is this positions a true background position? Same with this one. Do we have an effect of the tail of this peak or this one? We are not really sure if these are good background positions. There is also the problems again of the background curvature. And so far we have been constraining the curvature using a fixed parameter, an exponential or polynomial parameter. In this case, I propose you to actually acquire multiple points for your bremsstrahlung measurements. So here we have 4 or 3 points on the left side and 4 points on the right side. This might be doing too much, but there are situations where indeed you have this point like B4, where you don't know exactly if it is a good background. And effectively, if you look at the trend of all the points, effectively the point B4 is standing above the fit of this lower point. So B4 is probably not a good background measurement. You can also have what I would call a surprise element. Like for instance, you were measuring monazite, and suddenly you totally forgot that monazite can help sulfur. And you place a background positions very close to the sulfur lines that normally is not present in your standard, for instance, but could be present in an unknown. And so if you were to place your backgrounds B5 here, and suddenly this would be here a minor line of sulfur, if you were to analyze something that is suddenly abnormally sulfur rich, you will get the wrong measurements. So for that, we use here this multi-point backgrounds option. So this option is available here. And in these situations, all options are found down there. So we'll see it live. I should mention that we can still set also 2-point backgrounds, and that will be my last words, maybe if I have time. But in terms of versatility, a cool thing, maybe I should say right now, a very cool thing is that you can apply a different background type on different materials, different elements, and different type of analysis, like standouts or unknown. You could still acquire your standouts with the classical 2-point backgrounds, but with the same setting, you say the software that for the standouts, get my 2 points with this position that I define here. And when you switch to an unknown analysis, apply this setting for my multi-points. So let's have a look at this multi-point background. I will choose here a rather old setting that I had on my very old probe, which is now retiring in the UK, which is about monazite dating. So for this monazite dating, the big challenge is that we do have to measure trace amounts of, whoops, I don't find my folder, there you go. We have to measure trace amounts of lead, notably. And so what I did was to define here my new sample setup. Whoops, I should, sorry, define an, I'm loading here a previous setup just to show you how I did things. If I go in my element slash cations options, you'll find here that already here, the versatility of this software, I have applied the mean atomic number background corrections to most of my rare earth elements. All these rare earth elements, it's extremely difficult to find a good backgrounds, and the mean atomic number works really marvelously. Now, for the thorium, uranium, and lead, which are really my crucial elements, especially the lead, I need to have a perfect measurements for the bremsstrahlung. And so for that, I use these multi-point backgrounds. So the multi-point backgrounds is selected over here. We first decide how many points we would like to acquire on each side. Oh, when I see that John actually increased the options, you can now set up to 18 points. But 5 here is what I set. And you can set here the number of points on the high side. And then you have this option of iterations. So I'll come back to that in a minute, but basically here we acquire 5 points. And out of these 5 points, we will take the 3 points that yield the lowest background. And down here, I have my multiple options. So I can choose here my 5 entries. So if I want to modify my point number 3, for instance, I would click here on these options, change my background position to 75, let's say, and validate my choice. So this would be the options to set your different backgrounds, same again with the high positions. The question is, how do I get all these positions? Well, once again, you must rely on a collection of wavelengths scan. So I'm going here in the plot window. I can choose, for instance, a scan of my moisture being reference materials of monazite from Brazil. And here you'll see, oops, I choose the phosphorus peak. That's not the one I wanted. Sorry, I want to move down to my lead position. There we go, lead M alpha on spectrometer 5. And you'll see here my problem. The peak of interest is here. And without going into too much details, it's even more complicated because we have at least 3 elements that interfere. We have a second order lines of lanthanum, we have the edge of the thorium M zeta line, and we have somewhere down there some yttrium line. I can show you that here. For instance, if I plot the yttriums, you have the yttrium L gamma 2, 2, 3 down there. we have the thorium M zeta down here, etc., etc. So interference is one problem. If I zoom full again, and the other question is, where do I place my background? So again, I can potentially model my backgrounds and choose here different multi-point position. Like for instance, here I have my position number 1 selected. So again, these are the values that I have selected so far. And I can move my position and potentially see how much change it will apply to my curve here. So these dark blue lines here is the results of the fitting of the multi-point backgrounds. So this being done, once you have here a good set of positions, you can get your analysis. And in the end, you just need to process your data. So to process your data, you go in the menu Run here, and we have an options to display and fit the multi-point background intensities. And this is where you can cherry pick and really nicely fit your background. So here we have some results in some of my unknowns. So I have here the listing of all the data that I acquired. And I have done here the points that are present within this data, for instance, within these samples PR88. I can choose here different values, and I can choose here different elements. So we have the multi-point backgrounds for the thorium, for the uranium, and for the lead. And one cool thing is that if you want to double check, are these positions quite well fit? Well, you can just simply load your wave scan. I don't have a wave scan, I think, in these samples, but I have one in the Moassier to show you. I'm going to load a spectrum here of Moassier scan. And you can appreciate here if you have done a good job by placing your backgrounds. So this is here a very quick overview of the multi-point background approach. Again, this is a technique you may not need to use for every samples, every analysis, every element, but this is very, very nice in case of trace element analysis. So I think I'm going to run out of time. So I will maybe just finish with the couple notes that I had here in my PowerPoints. So yeah, maybe just a quick notes about the setting the counting time. It's kind of a weird way to do it, but that's how John Donovan designed it. For the multi-point backgrounds, whenever you enter a time for your backgrounds, for your high or your low backgrounds, actually the real counting time will be divided by 2. And the reason for that, if I well understand John, is that he wants to keep the statistics relatively similar to a 2-point backgrounds versus a multi-point backgrounds. And so if you acquire multi-point backgrounds, you will for sure have at least 2 points normally on each side. And so the statistics here is respected compared to the 2-point backgrounds. There are also options in the acquisition options. Maybe I should run through this super quickly. If I go in my acquisition options, you have here a summary of all the elements that are being analyzed. And that's what I was telling you about setting the different background acquisition. If I click, for instance, on my phosphorus, I could choose here to get my backgrounds on the standouts being acquired, for instance, with the off-peak position. Whereas for the unknowns, it will be acquiring using the MAN backgrounds. So I can validate this choice, and you will see here now the phosphorus for the standouts is acquired with the off-peak. Same for the lead, for instance. And lead, in that case, actually, I left it here with both the multi-points because I have a separate setup, actually, that I'm using for the standouts. But so this is a very nice versatility of it. And there is also another very cool feature, which is down here, which is called the nth point of peak backgrounds option. So these multi-point backgrounds take a lot of time to get acquired. So you may not want to acquire the backgrounds on every point. So what we do typically for monazite is that we choose a homogeneous material or a homogeneous domain. We acquire on the first point only the background. And then on the next points, we acquire only the peak intensity. So imagine you have 5 points. You will ultimately have actually 4 data points, the first point being just the backgrounds. So that's a very nice and cool feature that saves you time. And also, I should say that, again, to come back to the problems of background damage, monazite must be analyzed with an extremely high current, and we must absolutely count for a very, very long time. So if we were not to acquire the backgrounds immediately as we start the analysis, we would start measuring the backgrounds approximately at least 5, if not 10 minutes after measuring the peak. After this time, we will have already damaged the monocyte, and the bremsstrahlung intensity will be already too high. So by acquiring on the first point the backgrounds and on next points only the peak position, the peak intensities, we solve or we limit the problems of beam sensitive material. And so that's the slide again. It was in case it was not working, and I'll finish here with some brief word about statistics. You can read more in the paper that we wrote with John Donovan and Mike Williams and Mike Jashinovich in the microscopy and the macroanalysis. But again, like for the MAN backgrounds, we constrain the backgrounds by using multiple background measurements. So the overall uncertainty that you can see here is seriously improved as you consider more and more backgrounds. So we can achieve a precision that can be as low as 0.5% relative uncertainty at 2 sigma level. So this is really a marvelous technique if you want to get into trace elements analysis. And sadly, I don't have so much time, but the share backgrounds options is actually related to the multi-point backgrounds. So in these situations here, Carsten Goermann acquired this data in a scheelite, and he was looking at trace elements in scheelite. And you can see, for instance, here that he has multiple backgrounds. So 1, 2, 3, 4, 5, 6, 7 backgrounds. And each of these backgrounds are actually linked to one element. Like, for instance, 6 and 7 were acquired with the gadolinium L-alpha, 3 and 4 with the erbium L-beta, and 1 and 2 with the tungsten. And sadly, for Carsten, you can see that the point number 2 in the tungstens was on the edge of the tungsten peak. So we cannot use these backgrounds, but instead we can use the other ones. And so by eliminating these wrong backgrounds, you can still constrain here the overall change in background intensity as a function of your spectrometer motion. So I'm going to leave you here with my last slides. And this is here, yeah, maybe just to summarize what you need to consider when, which backgrounds should I use. My bottom line is that the 2-point backgrounds acquisition is kind of passé, almost. It's still required for some trace elements or minor elements. I would still recommend you to acquire your backgrounds, but it's sometimes very risky. So using the MAN backgrounds in simple materials where you just care about the major and the minor elements is totally fine. If you need really good precision, consider using the 2 points or the multi-point backgrounds. And again, a mix of everything is probably the best. And actually, it's sad that John is not here because one day he gave me the award for the most complex and convoluted run. But that's not my fault. He has a very versatile software. So voila.
Great,
Thank you for your
you.
attention.
Yeah, thank you, Julien. Amazing. And I think
Stop
it really
sharing.
showcases why having the software really can like unlock a lot of capabilities from your great hardware. And just a note for people that are not familiar, like a lot of the vendor softwares only have off-peak, or they have something called slope. Maybe one day they will catch up, but all these options are really only available in the probe software.
Point. I forgot to mention that, yeah.
So there are a couple of questions.
Yep, I see one actually. Yep. In your monocyte setup, so you analyze phosphorus, which is major elements. So actually, novelty.
Actually, let's fully always read them out, because later in the YouTube section, I think people will not be able to see that. So yeah, in your monocyte setup, you analyze phosphorus, which is a major element together with trace elements, or you're using 2 conditions, question mark, one for major elements and one with trace elements. So yeah.
That's a very good point. So effectively, you can run into problems with dead time correction. And so if you analyze your standards with a low current, 20 nanoampere, and your unknowns at a high current, so effectively, I do have different setups. I do use lower current on my standards. I don't want to burn them. And you need, when you go into trace element analysis, you need to consider carefully your dead time correction. So there could be another webinar, maybe Paul Carpenter. I don't know if he is here tonight, but Paul Carpenter would be a good person to speak to us about that. Now, that being said, I solved my problems with the phosphorus. I don't, well, for monazite only, I do not measure phosphorus by WDS. I measure it by EDS. And I do a combined EDS-WDS analysis because phosphorus is not so much important for me. I just need to know how much there is roughly. Aside of this, effectively, the measurements of phosphorus with WDS in monazite can be tricky because if you use a high currents, you will damage your monazite, and the phosphorus is the first element to diffuse away. So my recommendation in that case is to use the time-dependent intensity correction to constrain for this potential loss of phosphorus. But of course, you'll have the problems that as you lose phosphorus, you gain the other elements, and notably all the other rare earth elements will increase. So ultimately, maybe another approach would be a combined condition, which is something possible with probe for EPMA. You can potentially have a conditions where it first analyzes all your elements, your major elements with a low current, and then it stays on the same point, but get another analysis at high current, focusing only on the trace elements. But again, this would be another webinar, I guess.
Yep. Okay, there's another good question. So is there a rule of thumb for the minimum number of standards you would usually use to create a man background? And I think that's usually what people, I think setting up and getting comfortable with this technique is what people struggle most with at the beginning. And then I let you answer it properly. What I find is like there are a bit of growing pains at the beginning because you only ever looked at your standards at the beginning in terms of their major elements. And when you do man, you're essentially looking at ppm levels of other elements. So interferences is one thing, but you learn a lot about your standards. So sometimes you can find that, oh, actually there's like 300 ppm of an element that you never cared about for your major element analysis. So how many depends also a little bit like how good your standards are. But yeah, otherwise, Julien, what would you say?
I would say in my case, for instance, I'm quite unfortunate because I'm lacking of good standards that don't have any iron. It's surprisingly difficult to find. And in the case of the iron, it's kind of extremes. I have basically 2 points. So it's not good recommendations. I would personally go for at least 3 or 4. 3, you are never sure. I mean, 3 will be a perfect fit all the time. 4, it's better. But if I may, again, maybe just briefly share my screen, I can potentially show you something on my MAN background curve. I will not choose the monazite setup because it will take approximately 10 minutes to load the MAN background page. It's a complicated run. Let's take something simple. And I'm going to go here for my magnesium. I think that's a striking one. So magnesium here, I have a very nice curve. I can put the arrow bars, but this is after trimming a few standards. If I reload the default for these elements, there we go, 251. 251 is a synthetic firelight, and I have measured it with 2-point backgrounds, and actually this firelight has a few 50 to 100 ppm of magnesium. So you see how sensitive the MAN backgrounds is. So if you have only 4 points or 3 points, you may not be able to detect this small standard that have a little trace amounts of this element. So the more the merrier. Don't overdo it. Usually for 10 elements, I have a total of 12, 13, 14 standards. And like Annette said, if you have very good standards, notably pure oxides, that's great. And that's probably enough to deal with only 3 or 4 per element.
What I would add is also, it really depends kind of what you're analyzing. So what you always want is to have your calibration curve, of course, extend over the range of mean atomic numbers in your material. So if you have something like quartz, it can be relatively short. If you have like 15 different phases and they have like a wide spread, you need to make sure that it extends far out enough. And then a lot of these calibration curves have a little bit of curvature. And so then I would say like, okay, if it's a large range of Z, then you need more standards because you also need to make sure that overall your curvature is adequate. You can get away with certain things by using the blank correction, but again, the more you try to do like one size fits all for a very diverse range of things, I would recommend a little bit more standards. And so there's usually a little bit of an iterative process also where you just find out what works and what doesn't, and so you can trim it down. But yeah, you can make a perfect curve with 2 points. That never is ideal. Sometimes if it's a major element, then at the same time doesn't matter so much. But if you're trying to do trace elements, then it matters more. And then you really want to make sure that you capture all that. One trick I found, because I even applied it for quant mapping purposes to oxygen, and it can be a real drama to find like even your metals are oxidized. So there's barely anything in my standard collection that is oxygen free. But that's why you then can use this off-peak turn to man. So then I use multi-point backgrounds or just a good exponential background on a 2-point and create my man curve then for elements that I don't have great standards for. So that's another trick. And one thing that I also just quickly would like to mention, because I think a lot of people are not aware enough of it, is if you, and I just quickly share my screen and go into that. So we have all our standards in the standard database. And the standard database has an option under standard, list all standard names in average Z for 2 types. So if you do that, it spits out the list where all your standards show their mean atomic number. So I just copy that into an Excel spreadsheet, try to get an idea what the Z range in my materials is. If I don't know it and I already have some analysis from a previous run, when you do an analysis, it shows here in the analysis window your calculated Z bar. And so with that, you can kind of get an idea what the range in your samples is, and you can sort of look through your standard collection and pick some that for the high end and the low end and the intermediate ones. So that can be quite useful then to start the process. And then you will inevitably find out that this has 200 ppm of magnesium, and that has, and again, then you learn eventually like, oh, this one is really pure and works for a lot of things. And that's also where sometimes standards, you can put a gallium arsenide in or something that has like nothing to do with your geological materials, and that can be a great man standard for all your other analysis, unless they're interference corrections. Okay. So what are other questions? Andrew Lockhart asked, oh, Julien, which one do you want to, but you're muted. Julien, you're muted.
Yes, I'm muted. Sorry, I just saw here I made a mistake. Dominique has had a question, so I clicked on the quick answered while live. Do I understand that the MAN backgrounds correctly, that the backgrounds depends on the matrix, and this is the curve you define when measuring multiple standards that do not have specific elements? If this is correct, isn't the background always the same for specific minerals at least relative to the peak of an element? So that's the background is constant relative to the peak count per second in a standard. That could always be used. So yes, potentially, if you have the average atomic number of minerals, you could assume my backgrounds will be always the same. But you are dealing with a machine for which it varies on a day-to-day basis. You may have different efficiency of your spectrometers, of your detector, and all these count rates can vary a little bit. So that's something I wanted to see on the long term, and I do see small variations in my MAN background curve effectively. But if you accept an inaccuracy maybe of 500,000 ppm, maybe you can go with an old MAN background set, but I would personally not.
Yeah,
I would reacquire a new MAN backgrounds every time.
I heard from people that specifically if it's like all major elements, again, if you have 1,000 counts per second, like on some major element, and your drift in background intensities is 10%, but the background is like 2 counts. Does it matter? No. But again, it's like usually even when you acquire the standard curve, the MAN curve, remember that you only spend time on the peak. So in practicality, it acquiring these curves usually just adds like 20 minutes to compare to a traditional run, even though I have like maybe 5 to 10 more standards in there. So oftentimes, as Julien said, it's like, is that the best place to cut corners? Again, for major elements, it probably doesn't make too much of a problem, but then you get to minor elements. When you acquire this data, you will also see, depending on the X-ray line and the spectrometer, sometimes across your Z range, let's say 10 to 30, the curve is really flat and the absolute intensities are relatively low. And so you have very little change across the whole Z range. But then other X-ray lines, other spectrometer position, it can make a much larger change. So then not having the right standards, having it poorly defined, it can really affect the data differently. Okay. I don't know. We're getting closer, and there are a lot of good questions. Shall I quickly show the precision accuracy, and then I don't know, Julie, maybe you can also reply to some questions in the
I'll try to do my
Q.
best, but it's start to get late on my side. I need to leave relatively soon. Sorry.
Okay,
It's 8
I'll
p.m.
also
on my
try
side.
to
I
answer as far as I can, but I just quickly wanted to show quickly the how to test precision and accuracy because I didn't properly cover that. Okay.
So if you don't mind, Annette,
Oh yeah, go for it.
Do you mind if I leave you here for tonight,
No,
or?
no, I can take it over.
So
and
I think
thank you
people have
for.
I think people have our contact information. So if you need more information, we are always here to help. Again, Proper EPMA is made by a community of users, and we are here to help. So I hope you enjoyed the show. I'm sorry to leave you earlier. Annette, thanks again for organizing that.
And Julien, thank you for you're in a very different time zone. So thank you for being already like doing this and also everyone who's present from the European time zone. So yeah, contact Julien otherwise with questions, and I just quickly do that and I can answer other open questions. So feel free to put more in the Q&A.
All right. Have a good evening.
Okay. Bye. Okay, so a few words on how to test precision and accuracy in your data. So again, precision, it all kind of is really much controlled by your counting statistics. And so here I have the analyze window with like a whole range of analysis. And when you output your data, there's like export selected samples, the user specified format. You can always output and get the detection limits and oxide weight percents and analytical areas and relative percents calculated by the software and put it into a spreadsheet. Same when you output, if I output data from 4 standards, same thing, just need to select them. Then I can even have like the database values and the variance in the data output. But oftentimes we want to check that during a run, and there are many good ways to test that. So the first thing is that if you go into calculation options, and this is applied then to whatever entry we acquired at. So so this is really on a sample by sample basis. You can change things for multiple bonds just by hiding multiple bonds, but let's just do it for the last one. You can go into calculation options, and then there is a calculate detection limits and sensitivity. And I just select that. And when I say OK, and then say analyze, then it outputs information into the main window here in the back. So that's the first important thing. So there's a single analysis here, and it tells me what my detection limits for an element weight percent are at 99% confidence. And it tells me what my relative error is for each of these elements. If I have more than one, let's see here, at least 3 in it. And of course, as I just said, I have to turn that on. If I want to turn on for all and they're all the same type, I can just say select all and have it. Then again, it gives me even more information at different percentiles individually, and shows me all that information. Now, let's say I want to improve upon that. I'm not that happy. I want to see more, or it's like too good and I want to save time. Then a really great option is also that as long as I have 3 points analyzed, so sometimes at the beginning of a run before I actually analyze anything, I just get like 3 quick points with very short count times, just so that I have the intensities. And then I can say calculate projected detection limits. So I set that in addition, say OK, and hit analyze again. And then it outputs here in the back projected detection limits for different times. So if I analyze 0.16 seconds, 0.39, so that's what these here show, I get different detection limits shown. And so I can kind of see a little bit, and it shows it more for the minor elements here, but it really depends on what you're analyzing, if it shows you everything or not. You can kind of get a quick idea like, oh, okay, if I ramp it up and down, this is how my detection limits change over the course of my analysis. And the same for the sensitivity. So this is a nice quick way to see how my precision is doing with the data. And so it calculates all that. Same thing can be done to the standards. Again, exactly the same options available there. And we can look at that. Now, again, here in the background, and there it's usually just 1 or 2 elements that we analyze. Now, how do we check for accuracy? So we usually do that with standards, obviously. And so we have secondary standards. And one of the nice things in the software is that I can very easily switch standard assignments, and I can also have the option to very easily acquire intensities, not only on the assigned standards. So let's say I do, as you can see here, the assigned standard on the diopside is for calcium and silicon. So I calibrate the elements calcium silicon on the diopside, but the magnesium was actually calibrated on the spinel in this setup. So this is a secondary standard for my magnesium data, but this primary standard for calcium and silicon. And so when I now hit analyze, I get my data, I get a total, all looks great. And it shows me here now the published values, first thing. And so, of course, for the calcium and silicon, it has to be more or less perfect because, well, it's circular. That's how I defined it, that it's using these intensities to quantify it. But the magnesium, again, is calibrated on the spinel. And I see that my diopside analysis is very close to the published value for magnesium in this material. So I can play around with that, and I can always check against what the published value is in this data. And same thing, like when I look at the magnetite, where I only acquired iron data. So it's perfect by definition for the published value compared to that. But then when I go to the hematite, where I use this magnetite calibration, I actually see that I'm getting very good values relative to what is expected in this material. So that's a quick way to check the accuracy of my data. And then lastly, at times you don't want to, so at times I would just like, if I have a secondary standard that I want to monitor, sometimes I just run them as a like a primary one, like I run them as a standard. But sometimes you want to use just, you have a different secondary standard or something, and you want to run it like an unknown. And that's what we've done also in this run. So these are Bernie Wood, other spinels that we run at certain times in between. And I also analyzed a chromite standard from my standard collections as a secondary standard. And so if I just hit analyze there, of course, I get the numbers, and I could look and cross-reference to my standard database, but we're all lazy, and probe software always fulfills wishes where we request things. And so when you go into calculation options, there's an unknown sample is a standard. And so I can go in there, and if it's one of my standards that are in the run, I can, okay, bad example, I should have added it. So I just use the spinel instead, because I know that's in it. So yeah, and there I can just, the name has to match. So I just say, this is the spinel standard. And then when I hit analyze, again, in the back, it actually puts out the published data, and it calculates the variance. So here are the published values for the standard. Even though it was an unknown, I told him what to look for, and it shows me what the variance difference in composition is compared to what is expected. So yeah, both of these options, this way you can cross-check against your published values, as long as you have it in the standard database. So that's what I wanted to check and show you. And okay, so a lot of people have to leave because it's taking a little bit longer. So sorry for that. Again, this will be on also the YouTube channel, but let me just have a quick look what else is open in terms of question. And I hope what I just showed you answered that a little bit. So yeah. Okay, so there was one question going back to the man background curves, and specifically there's an option to use an exponent for the z-bar, and if we would recommend to use this. So this is a semi-new function version based on work that Aurélien Moy did. And so essentially what we found, specifically when we ran Monte Carlo simulations and otherwise, is that there is like at times there needs to be a coefficient applied to the fit in how it's being calculated. There's a paper about all this with Donovan and Aurélien that goes into that. So there is an option for that. I would recommend to use this. You can play with this option a little bit. You see that the values change ever so slightly. Again, it always boils down to what you're trying to do. It's an optimization. It's if I would hardcore go onto trace elements, I care really about the quality of my man fit. If it's all major elements, it practically makes no difference. Again, a lot of these functions in the software so that you can escalate. So I think it's worthwhile, but it really depends. But just play with it. Okay, there's another question. When you assign your man fits and you exclude some elements, your fits will not be saved for your next session. Is there any possibility to save your assigned man fits? Is that true? I guess you could always, again, when you load something in, you could just have a version where you reload all your man fits where you haven't excluded anything. The idea is a little bit that, yeah, if you excluded it, you don't want to, like, when you start a new run a new file, you don't want to import data that in the end you never use. So yeah, I would just like go to the original file that has your man fits and have a version of that file where you reload everything again. And then when you load that setup in, I would think that you should get all the data in. Otherwise, reach out to us. That might be something that could be implemented. What else is there? Okay. I think that is it for all the open questions. I hope I'm not missing anything. And yeah, then I will just thank everyone for coming and taking the time and taking a little bit longer time. And I hope you got something out of it. We have a forum where you can ask additional questions. There will be a recording that will be on YouTube, so you can revisit certain questions. I also always would like to point out that when you go into the dialogues, there's often a help button next to a function. When you click on that, if you have the software, it takes you to the forum and usually tutorial. If you hit the F1 button, it opens the correct part in the manual. So there's a little bit other ways also how you can read up more on it. Then, yeah, I hope this was worthwhile. There will be other webinars planned that give a more detailed look into other like trace element analysis, light element analysis, time-dependent intensity corrections, and so on. So please stay tuned. Consider showing up for those too, and also check out other small tutorials that are on the ever-growing probe software channel. And if you also, if there's something missing, let us know. But otherwise, be the change you want to see. If you feel like that you're good with it, but you want to share how you do something, record your own tutorial and we can put it on the channel. It's a software by users, for users, from users, and all that. Okay, good. Enough rambling. Thank you very much for coming. And I hope you have a great day. Thank you.